Hello everyone, my name is Lior Benjamin and I am a graduate student at the Technion. The topic of my talk is maximizing throughput in Flowshop real-time scheduling. This fundamental optimization problem has numerous real-life applications ranging from manufacturing to cloud and embedded computing platforms. This is joint work with Jing Li and Baruch Scheiber from New Jersey Institute of Technology, Cont'd from IBM Research Center, and Adas Shachnai from the Technion. So let's start. The general settings for our problem consists of a set of n jobs that need to be scheduled on m machines. Each job, Jj, has a release time Rj and a due date Dj. A job can be scheduled on the machines only between its release time and due date. Job Jj also has a weight Wj. Now, each job consists of m segments that need to be processed on the m machines in specified order. The first segment of each job needs to be processed on the first machine M1, while the second segment of the job is to be processed on M2, and so on. Also, in the Flowshop model, the ith segment of a job can be processed on the ith machine only after the I-1th segment of the same job completed processing on the I-1th machine. The processing time of segment I of job Jj is Pji. We note that job segments need to be processed non-preemptively on the machines. Also, we assume that the processing times of the segments, the release times, and due dates of the jobs are all rational numbers. At any time, each of the machines can process at most one job. Our objective is throughput maximization, meaning that we seek a feasible schedule of a subset of the jobs of maximum total weight. We note that the Flowshop model has been widely studied for minimizing the latest completion time of any job since the 1950s, starting with the seminal work of Johnson, which showed that makespan minimization in two-machine Flowshop can be solved in polynomial time. However, most extensions of the problem are strongly NP-hard. Therefore, later works studied approximation algorithms for the problem. Previous work in the Flowshop model is focused on makespan, flow time, or tardiness objectives. However, little is known for the Flowshop model in the throughput maximization setting, also called real-time setting. In this work, we give the first non-trivial results for this problem. Now, let's see an example. Here we have a real-time Flowshop instance with 2 machines and 4 jobs. Each job has 2 segments. We can see below the time windows for the jobs. The jobs J1, J2, and J4 have release time of 0 seconds and due date of 20 seconds. And J3 has a release time of 5 seconds and due date of 15 seconds. Also, we can see here the processing times of each segment of each job. For example, we see that the processing time of segment 1 of the job J3 is 2 seconds, and the processing time of segment 2 of J4 is 5 seconds. Now, we show an example of scheduling the jobs on the machines. We start by scheduling the job J1. We can see that its release time is 0, so we can start to process the job immediately. First, we need to run its first segment on M1. Only after the first segment completes on M1, we can process the second segment of J1 on M2. Meanwhile, we can start processing the first segment of J2 on M1. Note that we cannot process the second segment of J2 right after the second segment of J1 because the first segment of J2 has not completed on M1. Now we notice that we cannot schedule any more jobs. We cannot schedule J3 since its due date is 15, and we do not have time to process its second segment. Also, we cannot schedule J4 since its second segment takes 5 seconds, and we have 4 seconds left on M2 till its due date. Therefore, we have a schedule of 2 jobs with total weight of 17. Now, Let's see a better scheduling for the same example. We first schedule J2, then we schedule J3. Note that we cannot run segment 1 of J3 immediately after segment 1 of J2, since its release time is 5 seconds, and J2 completes its first segment after 4 seconds. Note that J3 finishes before its due date. After that, we can schedule J4, and then we schedule J1. We succeeded to schedule all the jobs with a total wait of 25. Now let's see some real-life applications of the flowchart model. The first application is scheduling in cloud data center. A cloud data center consists of a set of server clusters connected with clients through a network. Since all the resources are stored on the servers, clients generate resource requests from the data center. A data request consists of two steps: task execution, in which data is obtained from a disk or distributed storage systems and stored in memory, and then transmission from memory to the client over the network. When data requests have release times and due dates, a natural goal is to maximize the total number of requests that can be processed by the cloud data center in a given time interval. This yields an instance of max T in the flowchart model. The next application is scheduling in autonomous vehicle navigation. An autonomous car is a vehicle capable of sensing its environment and operating without human involvement. The human passenger is not required to take control of the vehicle at any time, nor is a human passenger required to be present in the vehicle at all. In the recent years, autonomous cars have been a topic of increasing interest, as many companies are actively developing related hardware and software technologies toward a fully autonomous driving capability with no human intervention. Autonomous vehicles rely on sensors, complex algorithms, machine learning systems, and powerful processors to execute software. An object detection application running in autonomous cars takes images from a front-facing camera as input and produces car steering angles, braking, and acceleration as output. Since the algorithm uses deep neural networks, each image is handled in stages. First, pre-processing the data in the CPU, then the data transfers between the CPU and the GPU, and then neural network computation in the GPU. The process of handling the images in real time so as to maximize the number of images processed in a given time window can be viewed as a max-T instance in the flowchart model. Our main results are the following. The first result is a pseudo-polynomial time 2m+1 approximation algorithm for max-T on M machines where M is a constant. We note that the ratio of 2m+1 is essentially tight for any m greater than 2 due to a known hardness of our approximation result for maximum weight independent set with a ratio of omega of m over log n. We note that a variant of max-T where for every job j the start times of all segments of j are given explicitly yields an instance of maximum weight independent set in M union graphs. An M union graph can be modeled as the intersection graph of M segments, meaning that each vertex in the graph can be represented by at most M segments on the real line. Two vertices are adjacent if their ith segment intersects. For this problem, there is a known hardness of approximation result for a ratio of omega of m over log n. This hardness result carries over to max-T in the flowchart model and M machines for any m greater than 2. Our main contribution is a polynomial time 9 plus epsilon approximation algorithm for max-T in the two-machine flowchart model, where epsilon equals O of 1 over n for an input of size n, where that's the number of jobs is n. In the remainder of this talk, I will elaborate on these two results, but before that, let's see two more contributions we have made in this paper. We showed that MaxT admits better approximations on some restricted instances of the two-machine model. In particular, we present a four-approximation algorithm for instances where all jobs have the same release time and uniform weights. We note that the problem of maximizing throughput on a single machine with the same release times and unit job weights is solvable in polynomial time using Moore's algorithm. Using Moore's algorithm as a subroutine, we obtain an algorithm that yields an improved approximation ratio of 4 for MaxT. For the special case where all jobs have the same time window and arbitrary weights, we give a 3 plus epsilon approximation algorithm for any fixed epsilon that is greater than 0. The algorithm partitions the jobs into two groups, large and small jobs. For the large jobs, the algorithm finds an optimal solution by applying Johnson's algorithm for make-span minimization in two-machine flowshot. For the small jobs, the algorithm outputs a 2 plus epsilon approximate solution by applying a greedy algorithm for the knapsack problem. The algorithm then outputs the better of the two solutions to yield a 3 plus epsilon approximation. These are the main results of our paper. Now, I will elaborate on our first two results, especially on the first one. Okay, so now let's talk about approximation algorithm for fixed number of machines. First, as the processing time, release time, and due date of a job are all rational numbers, we can obtain an integer values for these parameters by appropriate scaling. This allows us to discretize the input and consider all the possible occurrences of a job j in its time window between rj and dj. An occurrence of a job specifies the start times of all of its segments on the M machines in its time window between rj and dj. For example, let's say we have the job j1 with two segments I1 and I2. Also, we know that its release time R1 is 5 and its due date is 15. So we call J11 the first occurrence of the job J1, and it is defined by the start time on machine 1, which is 5, and the start time on machine 2, which is 7. Also, there is the second occurrence of the job J1, which is J12, and its start time on machine 1 is 5, while its start time on machine 2 is 8. Note that the number of such possible occurrences of a job is upper bounded by dj minus rj to dm. Now, we give some notation towards solving MaxT on M machines using a linear program. Let Lj denotes the set of occurrences of the job Jj. As we said, the size of Lj is upper bounded by dj minus rj to dm. Let xl of j be an indicator variable for the selection of the L occurrence of the job j in the solution. We note that the number of variables and the number constraints in the linear program may be as large as dj minus rj to the m for every job j, and is thus pseudo-polynomial in the input size. Our goal in the linear program is to maximize Wx, where W is the weight vector of the jobs and X is a relaxed indicator vector. We now define job clicks on each of the M machines as follows. For machine I, we examine the time axis from left to right and find among the segments that need to be processed on machine I a segment whose right endpoint is earliest. Let Z be the time point where this segment ends. We now define a click C consisting of all job occurrences whose ith segment intersects the time point Z. The next click is defined by the earliest endpoint Z prime of an ith segment of a job for which the following holds. there exists a job occurrence JKR such that the ith segment of JKR intersects Z prime, but JKR is not in C. As shown in figure 1, J51 satisfies this condition. Intuitively, the endpoints Z and Z prime in the definition of job clicks capture the maximum intersecting job occurrences in the time window Z and Z prime. Hence, a feasible schedule can only select one job occurrence in each click. We formulate the linear programming relaxation for max_t as follows. Maximize Wx subject to, for each click C, the sum of xl of j for each job occurrence L of job j in C need to be less than or equal to 1. This first constraint ensures that at most one job's occurrence is selected from each click. The second constraint is that for each j between 1 to n, the sum from L equals 1 to the size of Lj of xl of j is less than or equal to 1. This constraint guarantees that at most one occurrence of a job j is selected for the solution. The last constraint is that for each j and L, xl of j will be greater than or equal to 0. We note that the program can be viewed as a configuration linear program where each occurrence JJL defines a configuration of job J. Now, before I present the main lemma and the algorithm, we need to define one more term, namely the neighborhood of a job occurrence. The neighborhood of JJL is the set of all job occurrences that have a segment which intersects a segment of JJL. For example, the neighborhood of J24 includes J13, J12, and J41. The following is our main technical lemma. Let X be a feasible solution to P. Recall that X is a fractional solution, so there exists a job occurrence JJL satisfying that XL of J plus the sum of XR of K for each job occurrence JKR that is neighbor of JJL is less than or equal to 2 times m plus 1, where m is the number of machines. In the proof of the lemma, we first show that there exists a job occurrence JJL for which the following holds. XL of J plus the sum of XR of K for each job occurrence JKR that is neighbor of JJL is less than or equal to 2 times m. We consider here only occurrences of job other than JJ. For two neighboring job occurrences, JJL and JKR, we define the term Z of JJL and JKR. Also, we define Z of JJL and JJL to be XL of J squared. We prove the inequality using a weighted averaging argument where the weights are the values of Z of JJL and JKR for all pairs of job occurrences which have intersecting segments. Now I will briefly show the steps of the algorithm. The first step is to solve the linear program and find an optimal solution X for the linear program P. In the second step, we define I to be the set of all half open subintervals of the interval between 0 to 2m plus 1. We define a mapping psi between L to the power set of I such that for each job occurrence JJL, all the subintervals in psi of JJL are disjoint. We note that psi of JJL is a set of subintervals. Also, the total size of the subintervals in psi of JJL is XL of J, and none of the subintervals in psi of JJL intersects any of the subintervals in psi of JKR for all the job occurrences that are in the neighborhood of JJL. The mapping is constructed for one job occurrence at a time according to the hierarchical order induced by the main lemma. We first define this hierarchical order. The last job occurrence in the order is the occurrence that satisfies the inequality in the lemma. We then remove this job occurrence from the feasible solution to P. We still remain with a feasible solution to P, and we can apply the lemma again and find yet another job occurrence that satisfies the inequality of the lemma. We append this job occurrence to the order. We continue in this same manner until we order all the job occurrences. We compute psi of JJL for one job occurrence at a time from the first to the last in the hierarchical order. If we assign psi of JJL greedily, that is, we assign the leftmost collection of such disjoint subintervals, then it can be shown that the size of the image of psi is bounded by the size of L. This is because each job occurrence may increase the number of subintervals by at most one. The last step is to find an optimal point. For a point y in the half open interval between 0 to 2m plus 1, let phi of y be the subset of L consisting of all job occurrences JJL for which one of the subintervals in psi of JJL contains the point y. By the definition of the mapping psi, it is evident that the subset phi of y does not contain two job occurrences that intersect and also does not contain two job occurrences of the same job. Thus, the job occurrences in phi of y can be scheduled feasibly to yield a weight of w of y, which is the sum of wj for every jjl in phi of y. Let y star be the y in the interval between 0 to 2m plus 1 that maximizes w of y. We want to return phi of y star. Note that if the mapping is computed greedily, as we did before, there are at most the size of L squared values of w of y star. These values are determined by the right endpoints of all subintervals. So we can loop over all the right endpoints of the subintervals and find y star and return the phi of y star. This algorithm yields a 2m plus 1 approximation for max t on M machines. In the paper, we show that with a slight degradation of the approximation ratio, we can use our algorithm to obtain a polynomial time algorithm for two machines. We partition the jobs to three groups: small jobs, almost large jobs, and large jobs. Then, by intricate analysis, we show how to reduce the number of variables associated with the jobs to be of size polynomial in the number of the jobs with only a minor degradation in the quality of the solution. The resulting polynomial size linear program can then be solved and rounded in polynomial time to obtain an approximate solution with a ratio of 9 plus epsilon. Okay, these are our main results. Now let's talk about some directions for future work. For the flowchart model with fixed number of machines M, we showed in the paper a pseudo-polynomial algorithm. Is there a polynomial time algorithm for the flowchart model with fixed number of machines where the objective is max t? Another direction is to design an efficient approximation algorithm for general instances, namely arbitrary number of machines. We presented a 9 plus epsilon approximation algorithm for general instances for the two-machine case. Can we improve this approximation ratio? Finally, design approximation algorithm for max t in the no-wait flowchart model. In the no-wait model, each job must run its ith segment on the machine Mi immediately after its I-1 segment completes processing on machine Mi-1. Our preliminary study shows that better bounds can be obtained for max t in this model. So that's all. Thank you very much for attending this talk.